Hello, welcome everyone, um, and also welcome Wouter for coming for this webinar. And so, my name is Sandeep. I'm the director of Flowthermolab. So, what we will do is we will have first we will introduce about Flowthermolab, and then I will introduce about Wouter, and then we can have this the nice seminar on aerodynamics. Okay, so first, for those who don't know or who are new to Flowthermolab, let me give you a brief intro. Hope you can see my screen. So can anyone confirm that?
Yes,
Yeah, thank you. So, Flowthermolab is an online platform. If you are new to it, we are an education platform, online education on CFD and, computing on programming. And also we do a lot of consultancy services in the area of CFD. Oh, okay. So this is the main business model, and we are located in UK and also in India. So in UK we are inside the Ingenuity building or the UNIP, University of Nottingham's Business Park, and in India we recently started the office in Mangalore, in India, which is in Karnataka state, south of India, and we have our employees there. And what and just to give you a brief intro about CFD and how to learn CFD. Why I'm introducing this is because most of you who registered, or many people who registered for this webinar, also asked how to start CFD, how to learn CFD, and also this is what anyway we are doing. So I just want to give you a brief idea how you can start learning CFD. And it's all about fundamentals. You need to have very strong fundamentals in fluid dynamics, in mathematics, and all the basic subjects which you learn in your university. This is the core, and on the top of that, we need to learn more courses. So first of all, it's the fundamentals or the basics. So CFD fundamentals, you can learn fluid dynamics first, and we have prepared a course which is slightly different from the academic course on fluid dynamics. The content is the same, the core idea is the same, but it is more towards what is really required for CFD. We are focusing on that part. You can look into these courses. You can also learn the CFD foundation course, which is very important for understanding the numerics, finite volume method, finite difference method, turbulence models, and all those things. This is the basic. This is the starting point, fundamentals. Once you are all familiar with fundamentals, you can look into the tools. There are many tools in the market. There is commercial tools. There are open source tools. For example, Ansys Fluent, you have a course here. OpenFOAM, we can, from very basic to very advanced level, you can learn Star CCM, and there are many other tools which are in the market, which is useful for you. So I would suggest, once your fundamentals are good, start looking into the tools and learn it from scratch. This is what industry need. And then also improve your programming skills. So learn Python, because if you want to automate things, if you want to do coding, you want to write your own small codes, or you want to do some scripting, you need some programming language. So Python is good one. Matlab is another one. C++. So we have all the courses, whatever I'm listing out here, we have the courses on our platform. You can look into this. And then there are advanced topics. So moving forward, like automation is an advanced topic. So CFD of turbo machines, it is specific topic. You're specializing on one domain. So CFD of multi-phase flow, another topic, or solver development in open form. This is something, an advanced topic you can look into. Multi-phase flow, fluid structure interaction, machine learning. So all these are advanced topics. So you need to go from left to right. Don't jump into AI or machine learning and then learn CFD. So first make your fundamentals clear, then go step by step towards advancement. Okay, so this is one way. And if you want to look into these courses, just visit our website, flowthermolab.com. And we are also launching our fifth batch on the mentorship program. This is our flagship program. This is a live courses. The other ones which I listed is, learn at your pace. You can always watch it whenever you want. You can enroll. But this is our flagship program. This is a 6 months program, live program. We are starting it in January. So if you are interested, you can register it. for this program, and it involves live classes on all weekends, a lot of free courses you will get, which are on the platform for next 1.5 years, specialized workshops, mini projects to get hands-on experience. Then there is internship project for 6 months. You will be working in a group on an internship project, and that will give you a lot of experience on a real world problem. And we are also introducing from this batch onwards, the fifth batch, we are introducing HPC or cloud access. So you will be also getting our HPC. We will be teaching you how to use HPC. Plus, you get access to our cluster through cloud, and then you also have the placement assistance. So this is the best, the course or um, the program we have. This is our flagship program, and we started from basics to very advanced level. So if you are interested, you can register to this program. So and that's all, I want to introduce about Flowthermolab. Now let us go into our today's topic. So let me first of all introduce Wouter. Let me stop sharing my screen here. And yeah, so hi Wouter. So welcome, and
Okay.
thank you very much for accepting our invitation. And so about Voter, let me introduce him. He's well known on social media. He's well known in news, and for the fantastic product Airshaper. So Voter is the founder and CEO of Airshaper, a company based in Belgium. And the idea is that simplifies aerodynamic analysis through cloud-based virtual wind tunnel. So that's the specialty of the company. And he got expertise in mechanical engineering, CFD, and Voter created Airshaper to make aerodynamics accessible to industries like automotive industry, aerospace industry, and sports industry. And user can just upload 3D models and receive detailed aerodynamic insights. And such a revolutionary idea in CFD. So, and it was launched in 2018. And Airshaper is already recognized in the market. You can see it on LinkedIn, several posts, and people sharing about different ideas, what they created using Airshaper. And is like they won a lot of awards as well. So I leave it to Voter to introduce more about Airshaper, and also about today's topic aerodynamics, and hopefully it will be very useful for our students and all everyone who joined from industry as well. So over to you, Voter.
Thanks a lot for the introduction, Sandeep. That's very nice. Actually, I prepared a short presentation. I'll just go through, and through that presentation, I'll actually introduce Airshaper because the essence is that we do offer automation. So I'll send a request to share my screen. If you could approve that,
let
then
me
we
let
get
me yeah,
started.
yeah, can you try now?
Okay. And now, can you
Yeah.
see my screen?
Yes.
Okay, fantastic. So today's talk is about automation for CFD, which does help to greatly speed up your workflow. And if you move from academia to industry, it usually is mostly about time to market, efficiency. So get the best possible product out there rather than spending 5 years doing PhD level research. You want to be as pragmatic as possible. So automation really comes into play there. I took some parts from another presentation. I won't dive into the details too much, but just to frame what we're talking about, some concept will be relevant when we're diving into the details of automation. So, what is aerodynamics? So, as you know, it comes into play, also hydrodynamics, by the way, which is something we also do at Airshaper. Anything which has to do with transportation. So, airplanes, they need aerodynamics to even just stay in the air, otherwise, they can't fly. Trucks, there's a lot of push for more efficient trucks in different parts of the world to reduce their carbon footprint. Trains, of course, energy consumption, but also the way they enter tunnels, which can cause dramatic variations in pressure. But even super yachts, the comfort, the wind comfort when you're actually having your fancy dinner on the deck of your yacht. So it applies to many domains in transportation, but also the wind flow around buildings. The renewable energy, so we analyze whether solar panels will fly away or what the wind loads are on a structure, so you can then design the structure to be strong enough. Wind turbines to optimize their efficiency. But also athletes, your position on a bike, for example, we can go directly from 3D scan to fully analyze athletes to provide them tips on how to change their position, their equipment, and so on. And a very big topic these days, drones and UAVs also, of course, require aerodynamics to be optimized. You basically have two options. There are many more, but two main options to analyze and improve your aerodynamic performance. One is the wind tunnel, which is fantastic because you're working with real wind. It's there's not even a resolution because, well, apart from quantum physics, it's just a continuum, the air. You don't have to discretize it like we do in simulations. So that's really very useful. You can test different setups of the car all in one day if you prepare for this properly. So really interesting, but very expensive. And you can only do this as soon as you have something physically available. So you need to build a prototype, a small scale or a full scale prototype. So usually you would keep this for the later stages of design. And more we see that going from 0% when there was no CFD, we would easily be at maybe 80, 90% of the design work for most applications is being done using computer simulations, which is very interesting as well. You can test all kinds of crazy concepts without having to worry about safety, building it. Timeline is very short and so on. But of course, you need to control your simulation process because you can run a simulation in 1,000 different ways and get very different results based on what you put in. So that will be the topic for today. How do you automate all of these settings as good as you can? Now, why is aerodynamics important? I won't linger on this too much. You probably already have a good basis here, but aerodynamic forces, they scale with the square of the velocity rather than mechanical resistances, which are often even just constant. So that means if you take your Volkswagen Golf with around 125 horsepower and you can reach 200 kilometers per hour, you need 8 times as much power to reach double the velocity. That's because the actual power required scales with the third with the third power of the velocity, and that is immense. So as you can imagine, for airplanes and even rockets and so on, this becomes extremely important. When we talk about sorry, aerodynamic forces, we can typically split those into friction drag and pressure drag. So if you would integrate the force of the air on the surface caused by the air sliding parallel to the surface, this is your friction drag, which for low speed applications like cars and so on is usually just around maybe 5 to 20% of total drag. And the majority of the drag is coming from the pressure drag, which is when you integrate the force of the air pushing and pulling perpendicularly to the face. That's because most objects that we use to drive around, whether it's a motorcycle or a car or anything else, are actually not that aerodynamic. It's only when you go to planes that things become different, because planes have to go so fast and generate so much lift and be so energy conscious that they have to be extremely streamlined, which means that the majority of the drag is coming from the friction drag because the pressure drag has been reduced by quite a lot, at least in a relative way. So we'll get to that as well when we calculate forces in CFD. Drag coefficients, as you know, this is like a dimensionless number to quantify just how aerodynamic an object really is, irrespective of its size. At least that's the theory. In practice, you'll see that if you scale an object, the Reynolds number will change and your CD does not exactly stay the same. You'll also see that if you speed up or slow down, your CD is not entirely independent of your velocity. But for the sake of simplicity, this is the theory that is often used. And as you may know, a drag coefficient of a cube is around 1. A very streamlined body drop shape would be around 0.04. Again, this is all for a specific velocity and so on. Nevertheless, just this gives you an order of magnitude. The Reynolds number, also something which is quite important. This is not a real physical quantity. Very often you get asked, how do I calculate the Reynolds number for this application? Well, we don't know either because it's arbitrary. The reason being that you need a velocity. Usually this is the free stream velocity, but if this is like a local velocity around a small wing, which is on a bigger car, then what is your velocity? The length is a characteristic length. But what is the characteristic length? Usually it's like the length of a vehicle or the diagonal, or is it the wingspan? So this is all arbitrary. Nevertheless, this is a useful number to compare different cases in terms of what type of flow you can expect. If you compare an airplane, which is very fast and very big, to a miniature toy car, you'll have a very different Reynolds number, which means the flow separation will be quite different, even if you have the same geometrical shape in some cases. So if we move then to the next slide, laminar versus turbulent flow, also something which is quite important in simulations. Laminar flow is where your streamlines are staying nicely attached to the surface. They're all moving in a nicely parallel way. There's no randomness in the flow. Whereas for turbulent flow, it's full of randomness. You have your main flow, so the average velocity is going into one direction, which has a certain vector. But superimposed on that, the flow is kind of going all over the place. And this is what you call turbulence, small eddies and vortices, providing that seemingly random flow pattern. Flow separation is also quite important. So if you have this wing, if it's nicely attached, the streamlines will follow the contour of the wing. But if you have flow separation, imagine you would increase the angle of attack of your flow, then the air needs to go around and actually follow that sharp curvature. At some point, this is just becomes too much for the air, and the air decides to just go straight ahead instead of following the curvature all the way down. And this is what we call flow separation. The point where the surface and the flow, the boundary layer, they separate. This is flow separation, and you can imagine in the weight there, just below this flow line and the surface, you have an area where the flow is recirculating and so on. Just a few basic concepts on flow aspects in general. So we discussed the first option, physical wind tunnel testing. This is a very interesting option. I think this is Schumacher even. Basically, you're forcing air through a tunnel using a fan, and you put your object in the middle of that tunnel or somewhere in the tunnel, and you analyze the airflow around that object. The concept is very simple. It's very nice, as mentioned, because it's real air. You can test different variations and can be very accurate. But you need to instrument your model, so place sensors all over the place, sorry, to understand what you're seeing, what you're feeling, what kind of force you're measuring, and so on. And it's very, very expensive, not just to build the model, but also to rent a tunnel. A very simple tunnel without moving floor or anything, test section 2-3 meters or something, will easily cost you 5,000 euros a day. If you want one with a moving floor like the one we're seeing here and so on, it can easily go up to 5,000 euros per hour and more. And it's difficult to visualize what's going on. So you need to either release smoke or use laser systems and so on. All kinds of challenges also to get reliable values out of there. I know the concept sounds easy, but controlling the wind into the test section, there's all kinds of different elements and components that actually contribute to the accuracy of a wind tunnel. So very useful, but also very expensive to get it right. Now, one of the aspects in a tunnel, which are also valid for simulations, is the cross-sectional area. So if you put an object into a wind tunnel, the air has to go around it. And in real life, that's fine because you have space around your object in most cases. But in a wind tunnel, you have the walls and you have the floor and you have the ceiling. So that means if your object is too big, the air has to squeeze around that area. So if this is your car and this is the test section, I hope you can see my cursor, then the air has to actually fit through this area, which is lower than the area, the cross-sectional area of the tunnel without an object, which means the same flow rate will actually have to speed up to maintain a constant flow rate. So that means virtually the air is speeding up, which means that if at the beginning of the tunnel, your flow rate or flow speed velocity is 10 meters per second, around your car, it might be 11 meters per second. So you have to compensate for that using correction factors and so on, but they don't correct for everything. You still introduce errors into the flow because it's really just a different flow pattern. So this is what we call the blockage factor, which is the ratio of the frontal surface area of your object versus the cross-sectional area of your wind tunnel. And the recommendations, they vary. Some people say it has to be below 5%, others would say 10% and so on. In any case, keep in mind, you have to be realistic and you cannot test a car in a tunnel which is just 50 centimeters wider than your car. You're just going to get completely false results. And we will see that in simulation as well. Only the benefit in simulation is that you can automatically scale your tunnel to be very big without much additional computational effort. This is what we discussed, 5 to 10%. Another effect is what we call the wall effect. So even if your tunnel is big enough, your object will impact the aerodynamics, especially in the case of this airplane. The wings have a lifting effect, which will create a vortex around the wings. And if you have a wall, even if it's like 1 or 2 or 3 meters away, the wall will actually interfere with this flow structure, which in real life is much, much bigger than what you see here. Which means that if you put a wall there, you force the air to stop rotating there, which means you impact what is happening around the aircraft, even if your blockage factor is low. Sorry, I thought someone was asking something. So that is also something to keep in mind. It's not just the blockage ratio, it's also the proximity of the walls to your application. Other things, if you want to test in a wind tunnel, often you do a scaled test. But if you scale a model down, there's all kinds of similarity numbers and scaling factors that you need to take into account, which will impact your simulation. It's not just as simple as if you make a model at half the scale, theoretically, you have to double the speed. But it's actually more complex than that. There's all kinds of factors that will reduce the accuracy of your wind tunnel if you're working on scaled models. Sometimes they even use different gases just to compensate for some of these effects. So keep that in mind. And you need to measure things. In the virtual world, with simulations, it's easy to measure things. You can ask your data, please give me the total force, or please give me a slice of the velocity. In wind tunnels, you need special equipment to hold your object, to measure the forces, the moments, and so on. Nevertheless, it can be done and it can be very, very accurate. And we still recommend wind tunnels. I mean, as a final validation, in every single report that we run, we still say, please do execute a wind tunnel test because that is your most definitive validation. An illustration here of pressure taps, as you can see, could become quite complex if you want to wire all of these different points to like a pressure transducer to measure all of these pressure points and so on. And if you want to measure velocities, you can use laser systems and so on, but that can be dangerous for people. So all kinds of very cool options, but all with their pros and their cons. And before I jump into CFD, what I find really important is that, as Sandeep mentioned as well, if you're going to follow a track to become an aero engineer, I do think it's very useful to just get out of the books and the classroom and test things yourself. So, for example, you can find this video on our YouTube channel. We went out there, put some tufts, which are these small woolen strands on the car here. We just went driving with a small camera, just my cell phone. We filmed this and we saw how much movement we had, which is an indication of whether your flow is attached or detached and so on. Understanding the physics and really feeling the physics is, in my opinion, very, very important. Very good to have a theoretical basis. And on top of that, the knowledge on how to run applications, turbo machinery, and so on, as mentioned before. Great. But if you can really feel this, like develop an internal physics engine, let's say, I think that is really, really important. Then let's get to CFD. So maybe a quick word on CFD. You know all of this stuff, but just to summarize, we will also build a virtual tunnel around an object, and that virtual tunnel has a finite resolution. Just like when you're taking a picture, which has maybe a 4K resolution, in this case, we're just going to build 3D pixels, which is something we call cells. So the more cells you have, the smaller they will become, and the more accuracy you will actually get from your simulation. So that's really important to realize. This is never perfect, never ever perfect. Every simulation deviates from reality. Every wind tunnel also deviates from reality. It's all about being pragmatic and knowing or estimating how big your errors are, and to be as efficient as you can with the resources that you have. Which means if you're running a simulation, of course, you can just run every simulation at 1 billion cells and get a very good result. That's great. And again, that maybe fits well within a PhD or something. Nothing against PhDs, very valuable core research. But in industry, you might learn a lot more by running 100 simulations at 10 million cells, for example, even though it doesn't scale linearly, rather than running one simulation at 1 billion cells. So it's all about getting the best product out there within a reasonable time frame. So when it comes to meshing, for example, you'll want to spend your mesh in the locations where it matters most, which is close to your object where you have most vorticity and so on. We'll get to that later. So for CFD, once we have our grid, our cells, our mesh, basically, we will solve that set of equations. So every cell will have a number of equations that need to be solved. So for 1,000,000 cells, you have maybe 5 million equations that you need to solve, because every equation will link what is happening in one cell to the neighboring cells by linking the pressure, by linking the velocity, by exchanging data about flow rates, and so on. So there's a whole lot that you can actually do to still influence the accuracy, even once you have the mesh. It still needs to be solved. And solving this thing perfectly accurately is a complete overkill. So you'll actually make an approximation of the solution of this set of equations, which again introduces errors. So I've listed the errors here on the right. The first error is the modeling error. So you will solve equations, but those equations might not be the correct equations for your problem, or you may be ignoring things. Imagine you're running this motorbike. For example, if you ignore the thermal effects, even if there's no radiator, the small bit of compressibility in the air will cause temperature variations and so on, which impact the drag. Now, in most cases, you can neglect this. The impact is less than 0.1% maybe, but you're neglecting something. So the equations you choose to model your application, there you already introduce an error. That's your modeling error. Then you also have your discretization error, which is what we discussed. You don't have an infinite resolution. You always have a finite resolution. Plus, you need to translate your equations to a discretized version of those equations, which is an equation that can be expressed in your left neighbor, your right neighbor, and so on in terms of cells. So that's also an error you introduce. And then you have iteration error, which is what I mentioned. You will not solve the equations exactly, which would take a lot of time. You will just solve them until they're good enough. And to do so, you start with a guess, like let's say every cell has 10 meters per second, which is the same as the inlet velocity maybe. And then over time, every cell will start to talk to its neighboring cells, but hey, I need more velocity because it's impossible if the air needs to speed up around my helmet, for example. And this cell will say, wait, I'm in the wake, it needs to be lower. And all this starts to find an equilibrium. And this is a much faster way to get to a solution. And typically, you want to iterate until the error that you make with your iteration to solve the equations is actually lower than the errors that you have with modeling and discretization. So you just have to balance them to make sure that you're not overdoing it in one domain and neglecting errors in another domain. CFD automation. I'll just give you a quick demo of how Airshaper works, and then we can jump into the different steps that we actually apply. So this one, for example, is a sports car. What I did is I uploaded a 3D model of a car, and one of the main things to note here is that this car was not watertight. And by watertight, I mean that every 3D model can have gaps or holes in between door panels or overlaps of surfaces, or can be full of components. Like maybe there's like a gearbox assembly with 10,000 components in there or something. So we spent a lot of time to be compatible, with what we call non-watertight models. So usually CFD software will crash if you haven't perfectly closed everything. And typically the industry technique is to shrink wrap a model, which is literally like you would create a vacuum bag, get all the air out of it, and this will wrap around your model, and this will close small gaps and holes. Now, a problem there is that it might work well in most cases, but in some cases you're closing gaps which aren't supposed to be closed, or the other way around. So this introduces errors. So we spend years to make our platform compatible with non-watertight models, by just letting the air in the mesh leak to the inside, which represents a computational penalty because we need to calculate that flow on the inside. But because we control our own adaptive mesh refinement, we can limit that penalty and still have a fixed pricing strategy towards our customers. So we provide that clarity, fixed pricing, but in the background, that means we need to be very sure about what we're doing. Otherwise, we just bankrupt ourselves if we have to spend 5 times as much to run simulation. So you can upload models which are not watertight, it'll still work. And you can also upload models with up to around 10,000 components. So most of the real world effort to set up a simulation, like 30 to 50% is often spent on making the model watertight and simplifying it to take out all small elements before you can actually run a simulation. So this sounds like a boring thing, but if you're in industry and you want to be pragmatic, if you can cut that time out of your process, that is a huge gain. And that has a lot of implications on the entire automation sequence that we've built. Other than that, you can just select whether a model is on the ground or above the ground. If you do drones, it'll be above the ground. Virtually, we'll actually put it above the ground in the virtual wind tunnel as well. In this case, it's an object on the ground. You can select static, which is where a building, for example, is standing still and the air is moving across the building, or it's an object moving through the air, which means that the car is moving forward. In virtual simulation, the car is still standing still, but the air is coming across the car and the floor is moving. That's what we're doing virtually. And then you can also do hydrodynamic simulations. We do hydrofoils a lot these days, popular topic, and so on. You can select the velocity. You can change the pitch, roll, yaw, angle, and so on of your car. You can do side wind analysis. You set the units. Optionally, you can just detect the wheels. So the cool thing about our platform is that we actually try to remove any bit of friction to set up a simulation. So what I did now is to just restart the wheel detection sequence. And what's happening is that the software, it's already coming in, is automatically detecting the wheels. So that means we will detect the axis of rotation, which is this green line. We will detect the radius. And if we know the radius and that axis, we can also predict or calculate the RPM of the wheels because we know how fast the car is going. So just one click of a button for the user, and behind the scenes, again, a whole bunch of automation to come up with this. Similarly, you can also set up radiators. So if you zoom in on this one, sorry, this is a radiator, which is inside the car. The only thing we ask for is that you model this as a box. You can click it, and if you provide us 2 points on the pressure drop curve, which is the pressure resistance of your radiator, we'll automatically calculate the flow resistance and so on. And once this is all done, we again automate the entire post-processing, which means that we can analyze where drag is coming from, which are these red clouds. Basically, it's an isosurface for total pressure coefficient. We can analyze the surface pressure. We can analyze the surface friction, the surface streamlines, which you can then move around the car and so on. All kinds of visualizations that you can use to understand your problem, flow problem, and so on. And you can calculate the flow rate through the radiators and all of those components I mentioned. Even if it's 5,000 components, we automatically split all of those and just click on a component and you can analyze the forces. That's in a nutshell what Airshaper does. Now let's dive into the details as to how this translates into automation, at least the bits that I can share. Complex 3D models, as I mentioned, we can handle models which have not been made watertight, so you don't have to spend a lot of time. It also means that we can work directly with 3D scans. Very often these are STL files, which are just surfaces. Sometimes they have blind spots, which are not automatically closed by the software. We have worked with scans on full cars to analyze the competition and so on, right out of the box without actually modifying anything to the 3D scan. So that is possible. Of course, the quality of the 3D scan will determine the quality of your simulation. Even if the simulation is perfect, if you have a rubbish 3D scan, you'll get rubbish simulation data. But it's perfectly possible. And the high number of components, you don't need to spend weeks to take out all the small nuts and bolts of your model. The domain sizing. So we build a tunnel around your object, and there are a number of rules of thumb. I listed some indicative numbers, not the exact ones. I can't share everything, but first of all, if you would look at the front view of this motorbike, we automatically size our wind tunnel so that the blockage factor is actually less than 1%, which means that the effect is almost negligible. Still, nevertheless, for our virtual wind tunnel, we still apply a correction factor to compensate for any blockage effects that we may have there. In terms of the length of the wind tunnel, we would typically, by the way, a wind tunnel would be 10 times bigger than what you see here. This is just a snapshot. We would typically have 1 to 2 times the length of the object or even more upstream, because there the air is still clean and it starts to diverge around your object. Downstream, however, the air has been disturbed, you have a lot of turbulence, you have the wake behind your object. And even though this is 1, 2, 3, 4 times the length of the object downstream, this still impacts in a forward way the flow quality and the forces that you calculate on your object. So getting the wake right is very important. So there we go 5 to 8 times, for example, the length of the object downstream. And then there's the very special cases. If we do drones and so on, you may have a drone flying forward, but the drone has a jet of air going downward because it has vertical propellers, which are pulling the drone upward in turn. There it becomes quite complex, and we have different rules and sizing mechanisms to actually take into account that the jet is there and so on, so that we don't have a drone very close to the ground, because then you would have a ground effect, basically, if your walls of the tunnel are too close to the propellers. So there are a lot more complex rules to that as well. Adaptive mesh refinement. So we talked about the mesh. This is the very theoretical approach. We actually made this open source to some extent. We have a basic version which is open source on our platform. It's quite a bit more advanced. Nevertheless, you can implement this. We made an open source library to be implemented on OpenFOAM, where we refine both the volume mesh, which are the cells in space, let's say, and the surface mesh, which is the cells which are touching the surface. They actually create a surface mesh. Both of those are being refined in our system. And we have 2 types of refinement that we implement. So one is the wake refinement, which is whatever happens behind the object. So the air that you're dragging along, which is usually quite turbulent and so on. We refine that one based on curl of U. So curl is a measure for the vorticity or the swirl, the rotations in your flow, which is typically high in the wake of something. On the surface, we typically refine based on the gradient of pressure. This is where your pressure rapidly rises or falls, like around an airfoil, for example. You have a very dramatic change in pressure because you have the suction side at the top, which lifts your airfoil. You have stagnation pressure at the top. You have high pressure at the bottom, and so on. On our platform, we run various cycles of mesh refinements, but keep in mind, you can just download this, ask me for the link afterwards, and then you can implement this into your own OpenFOAM workflow if you like. This is a result of this. So this is a Formula One car. And here you can see the nice wake refinement that we have. So this mesh started out as a mesh which was just being refined as you got closer to the object. So this is part of the original mesh that you see here, this area of thick mesh density around the car. But then all of this here in the wake wasn't there in the first simulation. So we will run a 10 million cell simulation first at 5 million cells. We let it converge completely. We automatically analyze the gradient of pressure and the vorticity in the flow. And then based on the vorticity, we will actually refine the wake in a number of steps. And then you get this one. So you can literally see how the spoiler kicks up the air, because this kick of the air is actually where you have most disturbances, and those get refined. On the surface then, you have a high pressure gradient as the air comes to a standstill or near standstill around these side air pods, for example, around aerodynamic elements like the suspension and so on. That's where the pressure-based refinement really comes in. Now, when you run a simulation, typically you want to watch the convergence. And one of the industry standards, especially in academia, also in industry, is to watch your residuals. In our case, we opted to watch out for stability in the forces, because in the end, it's the forces, the real life forces that we're trying to predict, which are most relevant for our users. So if you look at this theoretical graph here, you could say, well, this is not stable yet. And as of here, it's actually stabilizing. So that would mean we would actually detect convergence over here and then say, okay, the simulation is stable. Now we can start to average. And averaging means that you will continue to run the simulation to average out any peaks and lows in your simulation to get a nice, reliable averaged value for the forces. But in this example, for example, right after we would detect convergence, it rises again. So our method will then kick it out of convergence and say, well, no, this was just a temporary flat. Restart your method, start monitoring from convergence again. And again, we get a flat bit. And this yellow window is actually the length of our evaluation window, which scales dynamically. And at point B, we have again detected convergence because the method says, well, it's been stable for long enough. Let's call it a converged simulation. And after B, we start the green window, which is to start the averaging process. And the more oscillations you have, the longer this process will take. And the length of this window is actually dynamic. So the more nervous your flow and so on, the more iterations we will run before we actually have the green dot here, which is to say this simulation has completely converged and we have a reliable averaged value. In real life, a curve can typically look like this. So very nervous, but there's actually a stable averaged value. We detect convergence here. We continue the simulation for another 596 iterations in this case, and then we called it completely finished. So that's the way we do this. Again, this one has also been made open source to some extent. You can download it from our repository and implement it yourself. In terms of post-processing, so once a simulation has finished, I'm now skipping the aspect where we have to schedule everything on the cloud. So we have a huge infrastructure and lots of software to schedule all these simulations on different servers. Whenever you order something, a new server gets launched and so on. I will not cover those aspects because you're probably looking to automate your own simulation. So post-processing there as well, we use ParaView a lot. So ParaView is an open source data viewing package, which allows you to load all of your data, like the forces, but all this, the pressure values, the velocity values, your turbulence model parameters, and so on, to load them all and actually do an integration if you want to analyze the force, or create an isosurface if you want to understand where pressure and drag are coming from, and so on. And throughout the entire sequence, we're actually carrying along all of those things that we mentioned. For example, if you have a complex model that you upload, well, we actually inherit the component structure of that model, which means that afterwards, the only thing you need to do is just click a component and you get the force on that component. So really intuitive to actually work like this if you have this level of automation. Yeah, then just some cool stuff before I dive into some cases. If you want to learn more, we have a video channel where we have a lot of videos where we explain things like the Cybertruck. So that's an example of where we used a complete 3D scan of the car, highly complex, and ran a simulation to understand the aerodynamics. And we were actually very close to what they officially claimed as a drag coefficient. The Aptera, it's a solar-powered car, which is really streamlined. Their official claim is a drag coefficient of 0.13, which is very, very low, and a range of up to 1,000 miles, which is huge. And then we have all kinds of applications related to electric vertical takeoff and landing, which is a new type of aircraft generation, let's say, that is in the making, or an industry that is being built in the hopes of finding a real market. And then we also did projects like this hypercar, where we completely modified, or the designer completely modified the exterior of the car, and we did the full aero package, which included front splitter, diffuser, underfloor, wheel arch ventilation, winglets, anything. We dropped the drag coefficient of the base Lamborghini by 27%. So that's huge, which allowed for a speed increase of up to 447 kilometers per hour. That's where we're at right now. So all kinds of really cool cases and things that you can actually achieve with CFD. theory can be quite dry and boring at sometimes, but the reality is really, really cool. I see that I'm running through these things quite at a high pace, but if you want to learn more, you can just you can visit our page, watch our videos. You can create an account at Airshaper. The account itself is free. We don't have free simulations, but the account is free. You can check some sample projects, which is what I'll do now. I'll just stop sharing it for just a second. Let's see. And I'll prepare some sample projects in the meantime. Any comments in the meantime that I should clarify about the things that I just said, not the general questions, but any aspects that weren't clear? I'm not hearing anything.
Yeah.
I guess you're all muted, but Sandeep,
Yeah.
is there anything
Yeah.
that you wanted to
Yeah. I mean,
remark or?
Hello.
few questions were there in the chat. We can take few of them, and then students also send a lot of questions. While registering, so we can also look into some of those questions which are interesting. So
Okay.
one interesting question from Maria is it's a standard question for any simulations when you run. So what for aerodynamic industry, or for automotive industry, for example, what range of error from between experiment and CFD simulation is acceptable for the numerical simulation, yeah,
Okay.
like 5% or 2% or 10%?
Yeah. I'm assuming you can see my screen again, right?
Yes, it is.
Okay. Well, I guess that there's two elements, like what is expected and what is accepted. So it really depends on who you ask. Very often, like I've been to some conferences where people would present like the latest advancements in CFD simulations, and they would all apply it to the exact same geometry, and still you would see more than 5% difference in calculated drag. Even though very often there are claims that, oh, we can calculate drag down to 0.001 percent correct or something. Well, I'm exaggerating, but down to 0.1% correctly or something. So it really depends on who you ask. What is also important is that you make a distinction between absolute errors and relative errors. If you have a very consistent workflow, and you can do so with automation, that's one of the benefits of Airshaper with automation in general. If your workflow is consistent, many of those errors are actually the same. And if you make relative comparisons between cars, to a large extent, they cancel each other out. So imagine you constantly overshoot drag by 5%. Well, if you're looking to improve the aerodynamics of your car, if all of your simulations have a plus 5% delta, that's never exactly like that, but just imagine, then it doesn't matter too much anymore. So very important to have a consistent workflow, which is realistic enough so that you can still cancel out the deltas between simulations. To give you an idea, one of our partners took a Tesla Model Y to the wind tunnel, and we also got a very precise 3D scan of this car. As mentioned, we can work directly with such scans. You could even read the tire marks on the sidewalls of the tires. Really, really detailed scan. And we had a delta of less than 6% between the measured value in the wind tunnel and the value that we calculated using our simulations. Now, 5% is still a huge deal. If your car suddenly has 5% more drag, that is huge. But again, we're talking about relative deltas. And what's also important to note is that it's not just a one number thing. So what's also important is the quality of the flow. So if you look at this image, this is a slice which was made 10 centimeters behind the car. And this one was done in the wind tunnel using PIV, or particle image velocimetry, which is the laser technique, one of the techniques to capture the pressure and velocity there. And the other one is the output of our simulation. And there you can clearly see, first of all, overall, a very similar picture. Second of all, order of magnitude, the same levels of total pressure behind the car. In terms of flow structure, you can also see that we captured these 4 vortices coming off the roof, which are there as well in the measured data. We do see differences close to the ground. Our lines here, they contour to a tangentially to the floor. In the wind tunnel, this is different, but the reason for this is that the wind tunnel only has a moving floor in the middle, through the wheels, in between the wheels, sorry. We have it across the entire width of our simulation. So that explains this delta here. But overall, a very good correlation. So to answer your question, yes, very often errors are to be claimed below 0.1% or below 1%. In reality, we do see some differences between software packages, but keep in mind that very often you're working on relative improvements of your car, and then it's important to just have a very consistent workflow. I'll jump to more questions later on. I've loaded the sample projects that I wanted to show you. You can apply this
Wouter,
also. Yes.
just one question which is connected to that, and then we can answer it. And so one is to get this 5% error, for example, in this very tight error. So what should be the typical mesh size, and what turbulence modeling approach you use for this?
Yeah. We use steady state simulations using K omega SST as a turbulence model. And in this case, we actually had a mesh of just 10 million cells. And you can always question yourself, is it by accident that I'm within 5%, or is it really that close? For that reason, you should usually, especially when you're optimizing your method, which you will then repeatedly use, to do a mesh sensitivity study, which is to run a simulation, let's say 1 million cells, 10 million cells, 100 million cells, 500 million cells, and then plot curves through those results, to plot your drag, to plot your lift in function of the number of cells. And if you see that they start to converge at some point, then you know that if for example, 100,000, 250,000, and 500,000, they all have the same result, they can probably conclude that your 100 million cells approach is actually good enough. But you do need to run that mesh sensitivity study. In our case, we did go to 100 million cells and also saw that the values were very similar. This can still be luck. You never fully know this. Every application is different. That is the hard engineering answer. Every application is different. So whatever learnings you have from the past are very, very relevant. But there can always be an exceptional case where, for example, a certain spoiler is only captured properly at 250 million cells, and you just overlook this because you stick to your 100 million cell approach. So it'll work in 90% of the cases, but keep in mind that sometimes you probably will overlook something.
This is also including the adaptive mesh refinement, isn't it?
Yes, that's the nice thing, because when we talk about a 10 million cell mesh at Airshaper, it's hard to put an exact number on this, but you could probably compare it to maybe a 20 cell mesh, which you create manually, because that one hasn't been optimized automatically to make the best possible use of every single cell.
Okay.
Just to run you through some examples, you can, of course, apply aerodynamics to rotating geometries. And in this case, it's a matter of automating what we call an MRF zone, which is a moving reference frame around your propeller. So that means you actually virtually, if you don't want to have like a sliding mesh, which is also possible, but more complex and time consuming, if you still want a steady state simulation with your propeller in one single place, you can build a cylindrical domain, for example, around your propeller, or at least a revolved object. Otherwise, it doesn't work properly. And then the size of this domain that you put around it is important. Because within that subdomain, you're going to calculate extra equations or solve extra equations, which take the centripetal forces and the Coriolis forces into account, which allow the software to develop actually a swirl and calculate the torque and everything. So again, in our case, it's all about automation. So we automatically calculate torque, thrust, and the power, and also the propeller coefficients in this case, behind this propeller or on this propeller. This is easy, but if you're looking at, let's say, an application like this, in this case, these propellers are actually very close to the support element here. So that means if you would build a cylinder around it to actually create this moving reference frame, it would cut or interfere with the static part. And if you don't solve that, you get all kinds of completely unrealistic flow. So what we've done is to create an automated method where this revolved object for the moving reference frame fits nicely around the static elements without actually touching them, so the user doesn't have to do this. And when you go look at propellers, it becomes really interesting. You can see that the pressure pattern on the drone is asymmetric. You have more lift on this side compared to this side because the propeller is actually introducing a swirl to the system, which changes the angle of attack left versus right here. If you look at the surface friction, this fuselage is actually in the wake of the polar propeller here. So you get a lot of increased surface friction. You can see that you have flow separation on this aerodynamic surface here, which is different on this side because of that swirl of the propeller and so on. And if you then move to your elements, you'll see that it's really nice to see the air being pulled into these elements. The polar propeller will accelerate the air and so on. You can also do internal flow simulations. And when it comes to automation there, for us, it's really important that you just need to set up a simulation with one click, and also the post-processing that you see here, which behind the scenes is using ParaView to a large extent, automatically shows you the streamlines going through a certain inlet or an outlet in the simulation. It's also about calculating the flow rates and the pressure buildup at a certain opening. Typically, you would have a manifold splitting the flow into maybe 4 or 8 separate tubes. And then you want to analyze the flow distribution across each tube and so on. So automation there really comes down to labeling all the patches correctly and automatically pulling that data and visualizing it for the users. This is a combined case of internal external flow, where we have a cooler unit, which could be on top of a train, for example. And there we automated the setup of the radiators and the calculation of radiators, and we automatically select the surface to visualize the velocity and the pressure across and through the radiator. But we also have fan elements, which are actually driving the flow outward. Sorry, they're pulling air through the radiator and then spilling it out at the top. So these also had this local moving reference frame to calculate the rotation and so on. And then the noise aspect becomes quite interesting. I saw someone asked about this. So we use an acoustic analogy, which is a set of, or actually one mathematical equation, which will use your turbulent kinetic energy field, which is turbulent kinetic energy is calculated for every cell in your domain. And then based on that mathematical equation, we can translate this into noise generation, which is an approximation because we only run steady state simulations. And we don't have a mesh which is precise enough usually to capture very small frequencies. So keep in mind, if you want to run a fully detailed acoustic simulation, you do need an extremely precise mesh, and you'll probably have to go to a transient simulation. Nevertheless, for large car OEMs and so on, we've been able to really reduce the noise, or at least provide them with lots of insights as to where the noise is coming from using this technique. Another case, which I haven't mentioned, is that you can also, let me use this one. You can also use CFD to not only analyze your flow, but you can also use it to assist you to improve the flow. And then there are two different ways that we offer this. Both are based on adjoint techniques, which is where a new simulation will be performed to understand the effect of surface changes on the drag or the lift of an object. And typically, the result of that, actually, I'll use this one. So on this aircraft, we asked the software to run this extra simulation to show us how we should move the surface to reduce the drag. For example, on these covers around the wheels, the red means move it outward and blue means move it inward. So red means that this tip here, if I look at the bottom view, this is a square box around the wheels. And as you can imagine, a square box is not the most aerodynamic element. So the design advice is telling us this is red, so move this forward here. And the edges are blue, move them inward, which means that if you apply both, you would get like a more rounded shape around these wheels. The same here around the cockpit. So the air will go, let me just scroll like this, will go around the fuselage, around the windows and so on, and then curl back inwards to fill the wake and the area behind the plane. So what the software is telling us, this rear part of the window, just squeeze it in already so that you have more of a drop shape and a tapered shape already, so the air can nicely flow towards the air at the back here. Also, you'll see that this corner here is quite sharp between the rear window and the tail, which is all normal for manufacturing constraints and for visibility constraints and so on. But from an aero perspective, you actually want to raise this, which will then smoothen out this radius. So this is what we call design advice, where the software is telling you how you should move the surface. What we can also do is go one step further and ask the software, well, then please implement these recommendations. So this is an airfoil, a basic NACA 15 airfoil, very short aspect ratio. And we asked the software, please optimize this for more lift. And it automatically changed like the profile and the shape of the entire wing there and increased the lift by a lot. So this is also something that we can do and something that we applied extensively to Aptera, for example, this solar-powered car that I showed you in the presentation. So this one, for example, by using this morphing, we were able to cut the drag before they watered it down towards safety and so on. We were able to reduce the drag by 15% on that car. Other things which are interesting, yeah, this is the same applied to the Ahmed body, which is a very simple shape. Most of you will probably know it. It's a very old reference object to test CFD codes, to test wind tunnels. It kind of represents a car, and this allows you to benchmark and fine-tune your code. And here again, to reduce the drag, it's suggesting this edge here is entirely blue, which means push it inward a bit so the wake can actually start to contract already. Same with the edge at the top. This is an angle, so the software is telling us, well, then push this edge down and reduce that. But it's not always like this. Sometimes you'll see something which is just very counterintuitive, and that makes it very, very interesting. And then I think I've covered most of the sample cases. In terms of other interesting documentation, if you want to provide an automated approach to people, it's of course important, like the previous question, how accurate is this, or how accurate should it be? The nice thing using this adaptive mesh refinement is that whatever object comes in, we will automatically tune our mesh to the specific flow pattern around that object or through that object, even if it's a pipe flow simulation and so on. Which means that without modifying anything to our simulation, apart from the fact that you can toggle the use of layers on and off, these cases have all been made using the exact same set of equations. So whether it's a drone that you're analyzing, and this is the correlation between wind tunnel and simulation for the drag curve, for the lift curve, or if it's a truck that you're benchmarking, and this is benchmarked against the European regulations that specify where you should be, and we're spot in the middle of the range that is allowed in terms of errors, or if it's compared to other softwares. This is Airshaper benchmarked against AVL, which is another software. It's nearly identical. If you zoom in, you see small differences, but it's very, very close. All of this is done using the exact same set of equations and automated approach. So that really is the benefit of automation. You save time because your sequence is automated, but you also have very consistent data, which allows you to compare things in detail. Other than that, yeah, there are some optimization cases and so on. I also saw some questions on how to build your career. So we get that question a lot. Sorry. So we made a blog on this. It's fairly old, but I guess it's still relevant. And don't take my word for it, because yeah, we are running a platform, a software platform. That's not the same as having an actual career in aerodynamics. I used to be a consultant there, and my path will be very, very different compared to your path. But as mentioned by Sandeep in the introduction, you need a very, very good solid basis. Otherwise, you can't build anything on top of it. But showing that you're pragmatic, I think, is always nice. Maybe I'm biased because that's the way I like to see things. But being pragmatic, dive into OpenFOAM yourself, start to study it, build your own prototypes, use tutorials online, follow a course, go out there, run some aero experiments at very low cost. All those kinds of things to show that you're very creative and pragmatic, I think, are important skills to have. That you just not only boast your theoretical knowledge in an interview, but that you say, well, I actually know what it's about, and I've played with this and this and this application. So this one I would recommend. You'll find the link in our blog. So blog here, if you go to one of the oldest, that is what you can find. If you go to Airshaper resources, I saw some questions on that as well. So we try to make an overview, even though we haven't used all of these. Useful resources to actually boost your aero skills. Some YouTube channels, some open source tools that are in there, open foam tutorials, and so on. We also have an open foam tutorial on how to use ParaView. So ParaView is an open source scientific data viewing package. I think I selected the wrong page. Maybe it dropped off. Yeah, is this one. So this video here allows you, it's free of charge. It's an open source software. So just create an account at Airshaper and go to one of the sample projects where you can hit the download button and download result data. Some of them still have the full open foam data. They can start to play around with that in open foam. Other than that, to boost your basics, I hope you like our videos. That there's quite a lot of videos. There's around 100, I think. The very old ones, if I just go to the last page, are about the theory. So what is a wingtip vortex, the Reynolds number, what is a drag coefficient, and so on. So if you're short on the basics, I would recommend studying these. And if you then move up in terms of time, you'll see some more applications, motorbikes, cars, bicycles, airplanes, drones, and so on, which will then provide you more specific insights for a specific niche on how to actually optimize the aerodynamics. So there's also interviews with Airbus. There's interviews with NASA. We also went to NASA 2 times to have a look at what they're doing and to cover this in some of the videos that you can see online on the platform. Let me just find some of those. Yeah, so this is one where we went to the Edwards Air Force Base to have a look at some of the really cool stuff they developed there, but also to interview the people who have worked on the X-57, which is an electric aircraft. And there's also one where we went to actually the site where they have the largest wind tunnel in the world, but we couldn't put that in the video, even though there is documentation online. But this is where they have the vertical motion simulator, which is a huge machine that takes you up and down in a room to actually pretend you're landing the space shuttle. That's why it was originally built. So lots of content. The blogs also feature a lot of content on various topics, how we use AI. There's a lot of questions on AI, so I'll try to reply to that already as well. So we also have a link between our platform and AI software. We don't have AI ourselves at the moment, but what we do have is an API, which is an application programming interface, which allows one software to talk to another software. So we have collaborations with people who have AI software. In this case, their software, which is Casey's, they can create parametric models, which means they can, for a propeller, they can change the radius, the pitch angle, the chord, and so on. And for every iteration or variation of that design that they can come up with, they can automatically launch a simulation at Airshaper. Airshaper will run the simulation and send back some data about the torque, the thrust, the efficiency, and so on. And then their surrogate model can learn from that and build a model which no longer requires simulations to be performed and actually can predict the performance of a propeller for new set points within the design space. To answer some of the questions that I already saw, it's important that to realize that AI is very powerful. I think it will play a crucial role in the future, already does so today. Today, it seems to be still reserved to applications where you have a narrow scope of a design space, like a car. You change the angle a bit, change the nose a bit, and so on. Keep in mind that you're training your AI system with points in your design space. So if you then ask that model for something which was not part of your training data set, or at least not close to that one, it needs to extrapolate, and then you can make very large errors. But if it's within the design space, for example, your spoiler goes up from 0 to 100 millimeters and you have training points in between, fine, you can predict those. If you train it with 0, 20, 40, 60, 80, 100, probably your prediction for 75 will be quite accurate. But if you ask it for the prediction of the spoiler, which is at 175 millimeters high, it might be off because it's extrapolation instead of interpolation. Nevertheless, I do believe that over time, AI will be used to speed up CFD simulation. For example, you can use a fairly accurate prediction as a first guess for your simulation, which means that you need way fewer iterations, like we saw, to detect convergence, because you start with something which is already quite close to reality, and then you use real CFD to actually fine-tune the final result. That could be very interesting, and maybe over time, with enough power, you can maybe build like a massive generic AI model for CFD, but that will still require a huge amount of data and training effort. So for now, the size of data set is usually quite large, 50, 100, 200 simulations that you need to train something. And you need to be quite close to your training data points, which means it's quite an investment. Which is useful for car manufacturers, for airplane manufacturers, and so on. But for everyday CFD use, if you're a consultant working on all kinds of problems, AI is not going to solve your problems straight away. But I do think over time it's going to be very powerful. You probably still need CFD as it's not a ground truth on its own, but as a training set for those AI models. And maybe over time, we'll see some hybrid approaches where you have maybe like a general AI model, which you can then fine tune with some simulations for your application, and so on. But yeah, lots of stuff to happening in that scene. And I think that's kind of it.
Wouter, I
So
think you
Sandeep, I
have,
don't know if you want
yeah,
to.
yeah, I think you have answered most of the questions. We had some 20 or 25 questions in the, which we selected, and I think most of them are correct, answered. But one I think is like on the LES. So do you need
Yes.
LES simulations for this kind of aerodynamics and acoustic simulations? So which I think you already answered in a way that you need to go for transient simulations and higher order simulations, maybe for more accuracy. But at the moment, I think Airshaper is dealing with only steady state, isn't it?
Yeah, we do. Theoretically, we could automate this to run LES or DES simulations. That's actually not too difficult. The only problem is that we would have to increase our price by a factor 10 or 20 or more, because they're
Yeah.
so complex. Those simulations in terms of computational effort are so demanding. That's why we're not doing this at the moment. But yes, if you want very precise acoustic predictions, then yes, you would need to go to transient simulations with a very, very fine mesh. But it comes down to being pragmatic again. We've achieved some great results with OEMs who had problems with wind noise around the car, inside the car,
Yeah.
and so on. And there, using our steady state approach, we were already able to point to some of the biggest sources of wind noise without actually spending so much money on the more complex acoustic simulations. But if you're dealing with like a specific frequency that is very annoying, like wind noise of a mirror can be very annoying if it's at a very specific frequency. Well, then for that one, you do need transient simulations and a very precise mesh and perhaps an LES simulation and so on, because steady state simulations are not going to predict that frequency for you.
Yeah. And one general question, I think most of them or some of them had this, like, what is the solver? Like, what is your engine? Is it open form? This was one question.
Yes,
One.
yes, our
Yeah.
platform is built on top of OpenFOAM. And then, as you know, OpenFOAM has hundreds of settings, literally hundreds and hundreds of settings, which you need to set correctly. And that's also part of the automation. So how do we set the turbulence intensity? How do you set the boundary conditions? All of those things are automated so that we have the best possible result, at least from our perspective.
Okay. I think we have covered most of the things, and time is also up. And I think thank you very much, Wouter, for your time. And I think it was very, very useful and insightful, talk. And and just for a few people who had some general question, like about the participation certificate, we can provide you the participation certificate. You just write it to support@flowthermolab.com, and you have seen like almost 200 people attended it. Sending everybody is quite time consuming, and we had a couple of weeks back another webinar, so few people might have there may be someone missing, and then you can, if you don't get any certificate, please write it to us and we can provide it. So, all right. So I think that's it. The general feedback, and Wouter, once again, thank you very much for your
You too,
time.
Sandeep, for setting it up.
Yeah, and see you soon.
Okay, thanks everyone. Thanks a lot,
Thank you.
and thanks for the questions. And if you have questions, just drop me an email, and we'll be in touch then.
Thank you. Bye.
Bye.